Today on Macaulay Math, we're using matrices to solve systems of linear equations. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 35 on matrices and systems of linear equations. Our goals for today: we're going to write and use matrices. We're going to use matrices to solve systems of linear equations in 2 and 3 variables. We're going to use matrices to solve application problems involving systems of linear equations. This lesson introduces the concept of a matrix. A matrix is very much like the movie that shares its name, but this matrix stores and manipulates numbers. It has many applications in statistics when large quantities of numbers need to be stored and changed. Solving systems of linear equations is a simple application of matrices, which makes it a good place to start. So let's get started.
Okay, so what is the matrix? A matrix is just a data storage device that can be manipulated in different ways to solve problems involving many numbers at the same time. Matrices are the plural of matrix, and Desmos has a separate calculator for manipulating matrices. Matrices by itself is a very large topic. We are not going to spend a bunch of time on it. In fact, we are only going to just scratch the surface on matrices and talk about how to enter data into a matrix and how to use it to solve systems of linear equations. But matrices has lots of applications outside of what we are using it for today. When you're talking about reading a matrix is defined by its rows and its columns. So you count the number of rows it has, and you count the number of columns it has, and that defines the dimensions of the matrix. So as an example here, I have a matrix that has 2 rows and 3 columns. That makes it a 2 by 3 matrix. Each of these numbers is called an element, and each element of the matrix is in a cell of the matrix. And these cells are designated by ordered pairs corresponding to their row and column. So this cell is in the first row, first column. This cell is in the second row, second column. And this element is in the second row, third column. The main thing that we're going to use for matrices is its inverse, and that we're going to use that process to solve systems of linear equations. And just like most operations have inverses, addition and subtraction, multiplication, division, square and square root, those are inverse operations. If you multiply by the inverse of a matrix, you can think of it as if you are undoing some of these operation. So to find the inverse of a matrix, you're going to use this x, and then it's not to the -1 power, it is x superscript -1, and that is a button unto itself, or you can put it in as if you were putting in a superscript using Shift 6 in the Desmos matrix calculator. The notation for finding the inverse of matrix A, and you can take this matrix A and denote it as an A inside of 2 brackets. And so the inverse of matrix A will be matrix A inverse. Inverse matrices usually involve fractions, so if you are asked to find the inverse of a matrix and you're using Desmos to do that, make sure you use the fraction tool to convert it to fractions. And also, one last thing, only square matrices have inverses. So we defined a matrix as a 2 by 3 matrix. This is a rectangular matrix. It is not square. Only square matrices have inverses, and you can have a 2 by 2 matrix that's square. 3 by 3 matrix is also square. All right, using matrices to solve systems of linear equations. And the way you're going to do that is you're going to take all of the variables and push them over to the side. And you say, wait a second, Mr. Macaulay, we've only done systems that have had 2 variables, x and y. But you can have linear equations that have more than just one variable. You can have as many variables as you want, It's just that all of those variables have to be to the power of 1. Now, I'm introducing some Macaulay-isms here just so that we can easily understand what we're talking about. And we're going to set up 2 matrices. It's going to be a square matrix that we're going to call the variables matrix. And the variables matrix only has the coefficients of the variables. So x and y is a variable, and a and b are coefficients of that variables matrix, and so a and b are the values that are going to go into the variables matrix. Then we're going to set up a constants matrix, and that matrix is not going to be square. It's actually going to just be 1 column in width, but depending on how many variables will tell you how many rows that constant matrix has. And that is going to be all of the values that have no variable with it. Hence, they are the constants matrix. And then what we'll do to make this solution is we're going to find the product of the inverse of that variables matrix. And again, the variables matrix is the coefficients of all the values of all of the variables and the constant matrix. And again, that's going to be this side of the matrix. As long as the product is defined, the result is the value of all of those variables, and that will be along the vertical, and you'll see that here very shortly. First, solve the system of linear equations using matrices, and we'll start with a very, very simple, straightforward one. In fact, this is one of the systems that we solved in the last unit by elimination. And so the first thing you're going to do is you are going to set up your variables and your constants matrix. And what that looks like is I have already got it. So the variables are all on one side, and I also have made it so that the variables all line up neatly in columns for myself. And so my first matrix, that variables matrix, will be just these coefficients for the x variables and the y variables. So I'll have 3, I'll have 2, I will have 4, and I will have -3. And you'll notice that this is a square matrix. And so if you have 2 variables in the equation, you're going to need 2 rows and 2 columns. You have 3 variables, then you're going to need 3 rows and 3 columns, 4 and so on, but we won't see any of those. Next, you're going to make up your constants matrix, and that's just going to be these values right here, 10 and 19. And everything has to stay in order. And then what you'll do is you will multiply by the inverse, and the result will be the variables in the order that you put them. So since we put x here, the x result will be right there, and the y result will be right there. All right. So that's really all we have to do to set up our solution. So let's go to Desmos. And this is the general graphing calculator that we have been using, but Desmos has a matrix calculator, and it is separate from the graphing calculator. And the way that you're going to get to that is you're going to hit Desmos, and then you're going to hit your math tools, and down here in the purple is matrix calculator. Now, if you don't want to go through all of that each time, you can just type in your search bar desmos.com/matrix and you will get it. All right, so we see some new controls here, and what we're going to want to do is we need 2 matrices. And you'll notice they have A, B, C, D, E, F, G, and H, and you can actually put in up to 8 matrices at a time, but we're only ever really going to need 2, maybe 4. And what we're going to do is we're going to hit new matrix, and the default position is a 2 by 2 matrix. But if you wanted to add rows and columns, you can either hit this plus button or you can hit the minus button, And since I need it to be a 2 by 2 matrix, that is what I'm going to start with. Now, if you hit enter at this point, it will put zeros in all of those and go down to the next line. All right, we don't want that. We want to actually enter in some data. So we're going to use the arrow keys on our keyboard to move this around. Now, when you hit the right arrow, it will move the cursor inside the matrix the same way you read. Left to right and then down a row. So let's enter the matrix that we had from the other page. And if we want, we can look back. It was 3, 2, 4, -3. So we'll go 3 and then right arrow 2, right arrow 4, right arrow -3. Now I have filled the matrix and I have all of the values that I want in it. So I'm going to hit enter and it's going to go down. Now anytime I hit this A button, it will consider this whole matrix that I already have in there. I'm going to hit new matrix again and I'm going to make my constants matrix. Now as I said before, the default is a 2 by 2 matrix. So I want it to be just a 2 by 1 matrix. So I'm going to get rid of one of those columns. I'm going to enter in the 10. Then I'm going to hit the right arrow. I'm going to enter in the 19. And now, because it's full, I'm going to hit enter. Now, to do the multiplication that I want to do here, I want to do matrix A inverse times matrix B. And then I'm going to get that result. So to do that, I'm going to hit the A button. I'm going to hit the inverse button. And then I'm going to hit the B button. And we see the result is going to be 4, -1. This result would be 4, -1. And we will enter our final solution as 4, -1 as an ordered pair. Put brackets around that. And we're finished. Now, a linear equation in 2 variables produces a line because it has 2 dimensions, length and width. A linear equation in 3 variables has 3 dimensions, length, width, and depth. Therefore, a linear equation in 3 variables will produce a plane. You can have systems of linear equations in 3 variables. In yesterday's lesson, we talked about ways that systems of equations in 2 variables could have no solution or infinite solution. For example, if they were parallel, there would be no solution. If the lines laid on top of each other, there was an infinite solution. Now, here's the thing. If you have a system of linear equations in 3 variables and you were just randomly making up numbers, you just picked 3 numbers for 3 equations, odds are that system is not going to have a solution. For us to have a singular solution, now the only way that that system of linear equations in 3 variables can produce a singular point of solution is if they intersect in such a way that they form only one point. Look at the room that you are currently sitting in. Look at the wall that is in front of you. Look at one of the side walls and look at the ceiling. That is an instance of 3 planes that intersect to form one single point, and it is in the corner. Many times, if you were to represent 3 planes, you'll get something like this, where you'll have infinite solutions, or infinite solutions when all 3 planes lie on top of each other. But there's even more ways where you could get no solution. For example, again, look at the room that you're sitting in. Look at the ceiling, look at the front wall, and then look at the floor. Those are 3 planes, and 2 of those planes intersect with each other, but there is no place where all 3 planes intersect together. So there are no solutions in that. You can also think of, if you're sitting on the first floor, the floor that you're on, the ceiling above you, and then the ceiling of the second floor, something that looks like this, those would be three planes that don't intersect at all and therefore have no common point. So what does that mean for us as we set up matrices and use inverses to solve a system of linear equations that have three variables? Well, we're still going to do it the same way. We're still going to set up all of the coefficients of the variables in one matrix and then all of the constants in a second matrix. Now, I've picked a problem here, and hopefully you notice right away by looking at it that there is no z in this second equation. And that's okay. Wherever you have a missing variable, you're just going to put a 0. So add So again, we're going to set up our variables matrix, and I'll have a 4, a 3, and a 1, a 6, a 1, and again, I did this problem especially like this so that you could see, since I have no z, I'm going to put a 0 there, then a 3, a 5, and another 3 for that last equation. We're going to take the inverse of that and we'll multiply by the constants, and this constants matrix will have a 14 in it, it will have a 9 in it, and it will have a 21 in it, and then the result will be x, y, and z. So let's go over to Desmos again, and you can do two things. If you hit clear all, you can start completely over, or you could go new matrix and change this to a 3x3 matrix, and we'll enter the data from the previous page. It was 4, then 3, then 1, and then in the second row it had 6, it had 1, and then it had a 0, and then in the third row it had a 3, a 5, and then a 3. We'll hit enter since we filled the matrix. Then we will have one last new matrix, and we will add a row and we will lose a column. We will put in 14 on the top, we'll put in 9, and then we'll put in 21. And since we filled it, we'll hit enter. And now we need to change because we need to take the inverse of C, the way that we've set it up, times D. So we'll go C, we'll hit the inverse, and then we will go just D, and then our result is 1, 3, 1, and we will finish this by making an ordered triple 1, 3, 1, and just like an ordered pair has x, y, an ordered triple has x, y, and then z. All right, let's do an application problem here. Mr. McCulley loves buffalo wings food. On one trip, he buys 2 orders of wings, 3 orders of buffalo chips, and 2 orders of fried cheese curds for a cost of $25. On another trip, he purchases 3 orders of wings, 2 orders of buffalo chips, and 1 order of fried cheese curds at a cost of $23.75. On a third trip, he purchases 4 orders of wings, 1 orders of buffalo chips, and 5 orders of fried cheese curds at a cost of $41.25. What is the cost per order of wings, buffalo chips, and fried cheese curds? Now, this example should look very similar to the one that we did yesterday, except instead of just 2 items that we are being asked to find the cost for, now we are finding the cost of 3 items. But you'll also notice that it takes me 3 different orders to calculate for those 3 different prices. So we'll go through and we will do it in order, just like the example yesterday. The variables are what the question is asking you to solve for. In this case, it is the cost of a wing, which I'll call W. I will call B the cost of buffalo chips. And I will call F the cost of fried cheese curds. Then we'll go through and we'll do it one at a time. So on the first trip, I had 3 orders of wings, 3 orders of buffalo chips, and 2 orders of fried cheese curds at a cost of $25. So if I go 2 times the cost of wings, plus 3 times the cost of buffalo chips, plus 2 times the cost of fried cheese curds, it'll cost me $25. Then on the second trip, it was 3 orders of wings, 2 orders of buffalo chips, and 1 order of fried cheese curds at $23.75. So 3 wings, 2 buffalo chips, and 1 fried cheese curd, and that one was only $23.75. And then the final trip was 4 orders of wings, 1 order of buffalo chips, 5 orders of fried cheese curds for $41.25. So 4 wings, 1 buffalo chips, 5 fried cheese curds, $41.25. All right, so we will then set up our matrices, which will be 2, 3, 2, 3, 2, 1, 4, 1, 5, and we're going to multiply that by we're going to multiply the inverse of this matrix by 25, 23, 75, and 41, 25, and that will give us a result of W, B, and F, W, B, F there. So let's go back to Desmos, and we can do 2 things. We can set up new matrices, or we can just edit matrices that we've already have. And I think that's what I'm going to do here. So I'm going to click on this 4 and highlight it, and then I'm just going to edit. So I'll go 2 right arrow, 3 right arrow, 2 right arrow, and then 3 right arrow, 2 right arrow, 1 right arrow, and then 4 right arrow, 1 right arrow, 5 right arrow. And you'll notice that it's already updating all of these values. And then I'll highlight in the second one, and that result would have been, it was $25 for the first one, and then it was $23.75 for the second one, and the last one was $41.25. And if I scroll back down, and you'll notice also the little fraction bar right here. If I wanted to convert them to fractions, I could, but since this is money, I will leave it as a decimal, and I can see that the result is $5, $2.50, $3.75. So we will write that out, and we will say wings cost $5, and then buffalo chips cost $2.50, and fried cheese curds is $3.75. All right. Well, folks, that is all I have. So, the Star Wars fun fact of the day: Mace Windu is the only Jedi to wield a purple lightsaber in the movies, although others have in the Legends universe. And, of course, the coolest color, purple, goes with the coolest Jedi, Mace Windu, aka Samuel L. Jackson. All right, that's all I got for today, folks. You have a great day. Goodbye.